Welcome to the session Advancing Open Source Statistical Frameworks with Rakshit GB and Dhanuj Lal from Fujitsu. Fujitsu is also one of the steering members of the UXL Foundation.
Hi, today my colleague Dhanush and I will be talking about our contributions towards advancing open source statistical frameworks, integrating VSL and OpenRNG for ARM-based AI workloads. We both represent the Monaka software R&D unit, part of Fujitsu Research India. To give a brief about Fujitsu, we have multiple research locations all over the world. We have two new research centers established, one in Israel that was established in 23 and the one in India that I represent from in 22. The Indian unit is mainly responsible for research in machine learning, deep learning, cloud-based data security, quantum computing, and so much more. We've also been actively contributing in open source projects like scikit-learn, TensorFlow, PyTorch, etc. We want to continue this momentum of contributing in softwares that accelerate HPC technologies. We've also joined UXL as a steering committee member since our goals strongly align with each other. We want to build a multi architecture, multi vendor software ecosystem for all accelerators, unify the heterogeneous compute ecosystem around open standards, build on and expand open source projects for accelerated computing. We've also been actively taking part in the special interest groups hosted by UXL. Fujitsu is also developing an ARM processor named FUJITSU-MONAKA. It is a data center CPU scheduled to release in 2027. The idea behind this processor is to reduce the energy impact by at least 60%. In the recent years, data centers have been growing exponentially, and there is a clear indication that it has to be developed in a sustainable manner. The only way going forward is to develop power energy chips to become carbon neutral as much as possible. To give more insights on this chip has many features, including many core architecture, confidential computing, and it is also built on the 2 nanometer node. It will be very highly performant, energy efficient, highly reliable, and easy to use. Fujitsu is also developing a software stack for this chip in parallel with collaboration with multiple entities like ARM, Lenaro, etc. We've also contributed in projects like 1DNN, 1DAL, and so many more to leverage this chip once it's out. So, coming to today's agenda, I will talk about a couple of things. I will introduce to what 1DAL is and the status of 1DAL on ARM, Fujitsu's contribution towards VSL kernels, introduction to OpenRNG, and our concluding remarks and resources. So, what exactly is 1DAL? 1DAL is a accelerator library initially developed by Intel and is now part of UXL. It is a data analytics library that provides building blocks covering all stages of data analytics. It is also providing an extension for scikit-learn for easy portability with Python related use. So enabling Wandal on ARM would broaden Wandal in more markets like mobile, embedded, and cloud. Wandal can also capitalize on the energy efficiency offered by the ARM ecosystem. Porting Wandal to ARM can help the library more adaptable. Opens up Wandal to a whole new community for new features and improvements. So the current status of Wandal on ARM is that it is available on ARM, but it is available on ARM only with SVE support. So the Neon support is still not available on ARM. And to talk more deeply into this, the way this was done is Wandal depends on a proprietary Intel component called MKL, and this was initially replaced with OpenBLAS, and that enabled Wandal on ARM. But there were several other components, including SparseBLAS, random number generators, VSL, and so many more. Some of these components had open source alternatives, and some of them didn't. In this case, specifically, VSL didn't have certain open source alternatives, and that would be the focus of our topic today. Enabling VSL would also bring in more algorithms to ARM and also optimize for algorithms as much as possible. The ARM version also has a lot of room for improvement in terms of vectorization and cache based tuning. So, to talk about the first topic, which is vector statistical library, VSL is part of the MKL component, and Wandal depends on few kernels from this subcomponent of MKL. And currently, there are no open source alternatives, and because of which there are no ways to compile certain algorithms on platforms that are not Intel. And VSL has subcomponents like random number generators, convolution correlation, and summary statistics. Vandal depends only on two of these subcomponents, namely the random number generators and summary statistics. To go deeper into what summary statistics is a group of kernels that compute routines like mean, variance, moments, covariance, quantiles, etc. It is a subcomponent of VSL MKL, and also there are no open source alternatives for this subcomponent. In the scope of Vandal, there are only 9 algorithms used from this subcomponent, two of which have already been contributed by Fujitsu, one of which is already merged, and one is a pending pull request. The first one is the matrix of cross products that would enable algorithms like covariance. This is the kernel that is yet to be merged, but the pull request has already been raised. The second one that was merged was variance unweighted, which basically enables algorithms like Gaussian mixture models. There are 7 other algorithms like outlier detection, quantiles, some second order moments, and so many more. All these kernels are open to the public for contribution to enable them in platforms outside Intel. To talk about our first contribution, we will talk about the sample variance kernel that we have enabled in Vandal. This kernel essentially computes the variance of a dataset, where variance is basically telling how far data is away from its average. Here in this formula, which is represented in its standard form, X basically represents the data matrix of dimension p cross n, and mu basically represents the mean of the ith dimension. This formula computes mean at every coordinate and computes the variance overall. This is a very tedious process and can be simplified as shown in the second formula, where the mean is not computed for each coordinates. Rather, the overall variance is achieved by finding the difference between the sum of squares and the sum itself. Here, S2 represents the sum of squares of each coordinate or feature point, whereas S1 represents the sum of the data point or the feature point. These are highlighted as shown in the loops below. The first image basically shows the for loop that's computing S1 and S2, and the second loop essentially combines all of this and computes the variance. Both these loops are simple and generic, and they rely on compiler for SIMD optimization. Now we will talk about our second pull request that is pending. We have raised this in Vandal community and are waiting for it to get merged. This kernel basically computes the matrix of cross products. This would be useful in algorithms like covariance, which basically tells the relationship between different vector points, or algorithms like PCA, which is used in dimensionality reduction. Here, the formula is represented as similar to the previous kernel, where X is represented as P cross N dimensions and mu is represented as the mean for both the ith and jth dimension. K here represents the number of samples. This can be further simplified into the formula shown below it, where instead of computing the mean at every point, again, the sums are used to tell how far away the cross products can be computed from. Here, S dash and N dash basically represents sum and total number of vectors until the previous patch, and S and N is the raw and total number of vectors including the current batch. Here, the concept of batching is introduced because for large data, the memory impact can be reduced if it's batched, and this essentially shows the computation from the previous and the current patch. And this full formula can be represented as a BLAS kernel. In this case, it's representing gem. So it can use either OpenBLAS or MKL to represent this. Now let's move on to the next topic, which is random number generators. VSL's random number generator provides interfaces for both pseudo-random and quasi-random vector generation. It also provides multiple engines, namely two Mazzane twisters, which is MT19937 and MT2203. It also provides another engine, which is multiplicative congruational generator. All these three engines are used in various algorithms across Vandal. It also provides three ways of parallel generations, which is family, skip ahead, and leapfrog. So far, these kind of interfaces are not available in alternative libraries in open source, and we need a similar or equivalent kind of library that would mimic this kind of behavior. So based on this, ARM collaborated with Intel and launched a new library called OpenRNG, which follows the MKL specification and was released in July 2024. It is also available inside the ARM-PL library itself. This OpenRNG library is not only compatible on ARM but is available for Intel as well, and it provides optimizations for ARM. And as seen in the graph below towards the bottom right corner, we can clearly see that the optimizations provided by OpenRNG is significant. If you take one example where the blue bar basically represents the data where OpenRNG is not enabled, and black bar represents OpenRNG enabled, it shows a significant speed up. And this example is from the dropout layer from March. And since it's also multi-threaded, as the number of threads were increased, the data clearly shows that there was a linear increase in efficiency. So based on this, the idea is that if OpenRNG can introduce performance improvements in libraries like PyTorch, it should technically also improve performance in Vandal, and that is why we wanted to propose OpenRNG as another alternative random number generator backend in Vandal. So as a first step, what we wanted to do was enable OpenRNG at a very high level in Vandal, and pull request for this is also raised in the Vandal community. What we did was we just changed all the build files, which includes compiler definitions, function definitions, and the makefile itself. We also introduced one new service file, which is service stat underscore OpenRNG, which is very similar to the existing service stat MKL file. This basically is an interface between what Vandal uses and what OpenRNG provides. So based on this, we were able to compile this on ARM and Intel, and we could see that it is providing the same interface was what MKL was providing. So we went ahead and tried to benchmark this, and we observed that the impact this OpenRNG had was little to nothing. This was mainly because all our algorithms was using the random number generator as a very small component as shown in the stack trace below, where most of the time is spent in the algorithm rather than random number generations. In terms of both k-means and kNn, there was no impact noticed, so there is more room for improvement for Vandal integration. So to conclude Open RNG, as shown in the table, MKL provides 3 engines and the standard option has only one engine as an alternative. OpenRNG introduces one more engine, which is MCG59. Only the last Mason twister is missing, and this missing engine could boost performance in algorithms like random forest, since most of the time is in that algorithm is spent in random number generations. So going forward, we feel that OpenRNG is a very good alternative and is open to the community for contributions as well. So that is why we are proposing OpenRNG as a alternative backend to the existing MKL RNG and standard RNG. By giving this as an option, users should be able to compile different backends at compile time. So to conclude, Vandal is available on ARM and is open to the community for contributions. VSL, there are total 9 routines, out of which 2 has been already contributed by Fujitsu and 7 are open to the community. Coming to OpenRNG, the new RNG library that is open source and supports both x86 and ARM. Fujitsu is contributing to AI ML acceleration for ARM-based CPUs. It aims to democratize AI with active open source collaboration. This slide basically highlights few of the resources. It highlights our pull requests as well as references to both OpenRNG and MKL VSL. You're free to take the QR code and see where each of these pull requests are. This project is also a NIDO project. NIDO basically stands for Technology Development of the Next Generation Green Data Center for the Green Innovation Fund project of Next Generation Digital Infrastructure. This is a project developed in collaboration with Japan.